Compressed air, a powerful source of energy in virtually every industrial plant. How is it used? Compressed air drives rotary equipment. It impacts, conveys, atomizes, sprays, sandblasts, agitates, and cools. It drives reciprocating equipment and operates control instruments. The speed, cleanliness, and safety of compressed air is being used more and more in all kinds of applications. The principles of air compression are easily seen in the operation of a simple bicycle pump. Hand power on the piston compresses the air. When the pressure in the cylinder is greater than the pressure in the hose, a one-way check valve opens and the compressed air is delivered to an air receiver, in this case, the bicycle tire. Differential pressure collapses the seal and admits more atmospheric air. Then the compression process starts all over again. There are two basic types of compressors. The bicycle pump is the simplest example of a positive displacement air compressor. The other type is a dynamic compressor. In positive displacement compressors, the air is physically squeezed by a piston or rotor. Compressing air generates heat. If the cylinder retains all of this heat, there will be a condition called adiabatic compression. Theoretically, 36% more power is needed to compress air when the heat is not dissipated. And intercooler and water jackets or oil jackets are used to remove some of this heat. If all of the heat is dissipated, this is called isothermal compression. A key diagnostic tool used in the industry is the PV, or pressure volume curve. This is a way to graphically show what happens during a compression cycle. The vertical coordinate represents cylinder pressure, and the horizontal coordinate represents cylinder volume. Inside the cylinder is a piston with a stroke ending at this vertical line. The space between the two vertical lines represents the clearance between the piston and the cylinder head. This clearance determines the mechanical efficiency of the compressor. A bottom inlet port and a top discharge port complete the schematic. Assume the receiver is under discharge pressure and the cylinder is filled with atmospheric air. Movement of the piston increases the cylinder pressure enough to open the discharge valve and release the compressed air. On the return stroke, compressed air and the clearance expands, and the inlet valve opens, filling the cylinder with atmospheric air. If all of the heat of compression is retained, as shown by the red line, we would see the condition we talked about earlier, known as adiabatic compression. But if all the heat is dissipated by cooling, we see a constant temperature in the cylinder, as shown by the green line. This, again, is isothermal compression. After cooling in a positive displacement compressor, the air may go through more compression and cooling to reach a desired pressure. 5 or 6 stages of compression can build up pressures of several thousand pounds per square inch, while minimizing the use of power. Next, the air passes through an aftercooler. The air is cooled again, and moisture is removed. Without an aftercooler, condensed water from the ambient air would flood the compressed air piping system. From the aftercooler, the air goes to a moisture separator. This separates the liquid from the air and then ejects liquid from the system. An air dryer removes additional moisture so that condensed water or oil does not form in airlines or tools. In a final step, the air goes to an air receiver. The air receiver eliminates pulsations, cools the air further, and then stores it for a steady source of compressed air. There are several types of positive displacement air compressors. In a reciprocating air compressor, a piston squeezes the air. These compressors may be lubricated, non-lubricated, oil-less, air-cooled, water-cooled, single-acting, double-acting, or multi-stage. Typically, power for reciprocating compressors ranges from 1/3 horsepower up to 600, with outlet capacities ranging from 1 to 2,600 cubic feet per minute. Pressures range from 30 pounds per square inch gauge up to 5,000. Another popular type of positive displacement compressor is the rotary screw compressor. These compressors are either oil-flooded or oil-free. Regardless of which type you are dealing with, the basic operation is the same. A male rotor acts like a piston, pushing air along a female rotor, which is like the cylinder. Air is compressed against the end plate and exits through the discharge port. Let's look at the basic steps in the compression cycle of an oil-flooded rotary screw compressor. Compression begins as air enters the housing and the rotor shafts begin to rotate. As the lobes and grooves intermesh along the length of the rotors, air volume is reduced and the pressure rises. Oil is injected to absorb much of the heat generated. The mixture of compressed air and oil exits through the discharge port on its way to an oil sump or separator. Finally, a coalescing lubricant and air filter remove most of the remaining oil and return it to the system. The air exits and flows on to the aftercooler. Oil-flooded rotary screw compressors have a capacity range of 6 to 3,000 cubic feet per minute. Power ranges from 3 horsepower to 700. Single-stage units can deliver discharge pressures of 50 pounds per square inch gauge up to 200, but are generally used in the 100 to 150 psig range. In oil-free rotary compressors, no lubricant is used in compression, so the air is oil-free. This eliminates the need for an air-oil separation system. Dry and water-flooded rotary screw compressors are similar to the oil-flooded systems. Capacities for medium-range two-stage models range from 200 to 4,100 cubic feet per minute, with horsepower of 50 to 900. Low-pressure single-stage units have capacities as high as 7,000 cubic feet per minute. Both air and water-cooled units are available as well. Two-stage rotary screw compressors may be used for improved efficiency or higher discharge pressures. Another oil-free compressor is the lobe type. It has 2 intermeshing lobes per compression chamber, rather than screw elements. These have capacities from 100 to 330 cubic feet per minute and 25 to 75 horsepower. They are also air or water-cooled. One other type of positive displacement compressor is the vacuum pump. It can be reciprocating or rotary in design. Vacuum pumps create a vacuum at the intake, pulling air out of a receiver tank or piping system and then compressing it up to atmospheric pressure. Vacuum pump capacities range from 35 cubic feet per minute up to 4,000. They can generate vacuums up to 29.8 inches of mercury. So far, we've discussed positive displacement compressors, which raise air pressure by physically squeezing the air. Now we'll look at dynamic type compressors. Instead of reducing the volume of air, these create pressure by moving the air through the impeller at a high speed and then controlling its deceleration. By far, the most common type of dynamic compressor is the centrifugal. As the high-speed impeller rotates, air enters the center. The speed imparts high velocity to the air as it moves outward into the diffuser. Here, much of the velocity is converted into pressure by controlling the deceleration. The high-pressure air is collected and flows to the outlet. Usually, 2 or 3 stages are used to achieve a compression of 125 pounds per square inch gauge. Centrifugal compressors are often thought of as high-volume flow machines, with capacities up to 200,000 cubic feet per minute. In recent years, however, new designs achieve flows as low as 400 CFM. No matter which type of compression system you work with, it's important to understand basic terms used in the industry. Atmospheric air has a constant pressure of 14.7 pounds per square inch when measured at sea level. Since sea level is a constant, all air pressure gauges are calibrated to register atmospheric pressure as 0. This gauge pressure is used most often and is abbreviated PSIG, or pounds per square inch gauge. You may hear engineers refer to pounds per square inch absolute, or PSIA. This is equal to gauge pressure plus 1 atmosphere. So, a gauge reading of 100 PSIG has an absolute pressure of 114.7 PSIA at sea level. Another important term is volume. It is measured in CFM, or cubic feet per minute. But keep in mind that volume can be defined in a number of ways, and these may be substantially different. Standard air refers to the volume of air produced by a compressor under a set of conditions agreed on by the buyer and seller. It is measured in standard cubic feet per minute, or SCFM. When considering the capacity of a compressor, do not confuse pressure and volume. Both airflow and air pressure are required to do work at the point of use. It is vital that all those involved in the design and purchase of compressed air equipment agree on the operating conditions that the equipment will face. This will avoid frustrations later. When working with compressed air, it's important to understand the difference between pressure dew point and relative humidity. Both measure the water vapor content of air, but they are not the same. Pressure dew point is the temperature at which vapor begins to condense as air is cooled at a given pressure. Relative humidity is the amount of water vapor in a given volume of air at a given temperature and pressure. It is expressed as a percentage of saturation. Saturated air has a relative humidity of 100%. The Compressed Air and Gas Handbook is a valuable tool that will help you to better understand the design and operation of compressed air systems. And for the highest technical performance, consult the ANSI and ISO standards, available from the Compressed Air and Gas Institute. We want to help you tap into an energy source that is reliable, efficient, and cost-effective. CAGI and our members offer you a wide range of resources and expertise so you can discover the power of compressed air.